last theorem. Congratulations, we have come so long. It is long divergence theorem. So divergence theorem, good news, is much easier compared to Stokes theorem. Okay, it's much easier. In this case, you have a sphere or generally a surface as a closed surface. Remember, the surface over there is not closed, therefore you have a boundary as a curve. All right? So in divergence theorem, our basic objects is a closed surface bounding a solid in the interior. Okay? So there is a closed surface S bounding an interior solid region D. Okay? So D is a solid region in R3 with boundary as a closed surface S. All clear? So these two are two different geometric setups. One is a surface with boundary as a curve. This one, we have a closed surface as boundary of a solid. Okay? And then any surface integral of the vector field. Okay, so we're still talking about the flux. It's going to be equal to the triple integral of the interior. Okay? So this is the divergence theorem, which is the second version of fundamental theory of calculus. So in this version of fundamental theory of calculus, we still have to specify what is in the interior, what is on the boundary. But this is pretty apparent to you, right? Interior is going to be the triple integral domain. Boundary is going to be the surface integral domain here. Okay? And you can still interpret this as the flux of the vector field coming out of a particular surface. And this divergence is going to talk about whether this is a source or a sink. So if you sum them together, whether it's a fluid coming out of this closed surface or there's a fluid going into the closed surface. Okay? But overall, in our calculus 3 class, our main concern is how to utilize this theorem to solve some problems. Okay? And the most important, definitely the most important example is you have a sphere bounding a ball. Okay? This is the most important example in Calc 3 in terms of divergence theorem, because this is the easiest example. Sphere is the easiest domain, as the triple integral domain is still the easiest. So the boundary is a sphere, the interior solid is a solid ball. Are you with me? So this is the region. So D as the ball in the interior, S is the sphere on the boundary. I still want to quickly remind you there is a slightly different notation here. So this is the same surface integral, but slightly different notation. And for divergence, remember we have this notation of the dot product. Okay? So this is our divergence theorem. So the surface integral, or if we begin from the interior, is a triple integral in the interior equals surface integral on the boundary. Okay, which is our fundamental theory of calculus version 2 in R3. Okay, so two versions in R2, two versions in R3. So we are pretty much finished about all the discussions about calculus 3. Okay. Again, every time if you talk about the integral, you have to be very specific. What is the integrating function and what is the integrating domain, right? Regardless of whether you're a single variable or multivariable or any variable, any integral you have to be very clear about where you're integrating the function and where you're integrating. So triple integral, the integrating function is the divergence, and the domain is the interior as a solid region. And surface integral, the integrating function is the vector field, and the domain is the boundary as the surface. Okay? Okay. There is, however, one thing I haven't talked about it. Because every time if we're doing a surface integral, we have to fix the orientation, right? So the orientation for the closed sphere or closed surface, you have either it point inward or pointing outward, okay? So in this case, the normal vectors are all pointing outwards. So in this case, all the normal vectors are pointing outwards, okay? And in this class, we are mostly interested in using triple integral to evaluate a surface integral. So I'll give you two examples what will be done for the whole semester in terms of problem solving. Okay? I have to say, I'm very excited today. And I'm right at the very last page of my So, x squared plus y squared plus a squared is equal to 4. My function is equal to minus y cubed minus x 5x cubed plus 4y minus 9y squared minus 8. I want to use triple integral to compute the surface integral of this vector field. Okay. I want to use the triple integral in the divergence theorem to evaluate this surface integral of the vector field. Okay. So again, if you want to use the sphere parameterization, you want to evaluate this guy directly, it's not going to be easy. It's actually quite challenging. Your vector field is pretty difficult. You need to come up with the parametric equations of the sphere. You need to compute the normal vector, which in this case is pretty hard to determine, right? The normal vector on the upper half of the sphere is pointing upwards. The normal vector on the lower half of the sphere is pointing downwards because our notation for the normal is always pointing outward. So it is outward of the region, but it can be pointing up or down. You have to set up two parts of the surface integral to be evaluated separately. However, if I'm using a divergence theorem, this guy is extremely easy. Since we're so good about triple integrals, right? This is nothing about the triple integral of the domain as a ball centered at the origin with radius 2 of the divergence of the function. And the divergence of this function, even though you look at each component, it might be complicated, but the divergence is actually super easy. The divergence of the function is equal to partial x hitting on this f component, partial y hitting on g component, and partial z hitting on h component. So I get a -1. So let's make sure everybody is on board. So I'm doing a partial f, partial x, plus partial t, partial y, plus partial h, partial z here. Okay? That's the only thing we're doing. And by computing the three derivatives, we have -1 plus 4 minus 1, which is simply 2. So the divergence of the function is 2. The region is a ball. We're doing a triple integral. Which coordinate system do you want to use? You want to use spherical coordinates. Spherical coordinates will be very frequently used once you have your domain to be a piece of a ball, or the function contains x squared plus y squared plus z squared. Okay. Now, if you look back at your whole career in Calc 3, now you probably like triple integral, multi, and double integral much more. Right? When you are in the middle of learning this, you hate those different systems. But now, once you are good at this, you actually love them. Right? The domain is a ball, so I'm going to go for 0 to 2 pi, 0 to pi, and 0 to 2 dv, or I'm sorry, 2. We have rho square sine phi as an extra factor coming out, d rho, d phi, d theta. Okay? So what do we have? Sine phi integrate from 0 to pi will give me a 1. Theta integrate from 0 to 2 pi will give me a 2 pi. 2 rho square divided from 0 to 2 is going to be 3. So this is going to be 3 rho square 2 evaluate from 0 to 2 pi multiplied by essentially just 2 pi. So it's going to be 2 cubed, 8. So 16, 32 pi divided by 3. Okay, hopefully we're correct in terms of computation. Am I? Did I make any mistake here? So I think I have 0 to 2, so 2 rho squared, so the antiderivative is rho cubed divided by 3, multiplied by 2. And then I need to multiply 2 pi from the integration of theta. I also need to multiply by 2 for the integration of phi. So I have to multiply by 2 in the end. Okay? Again, this is not the key points for the whole problem in this section. Of course, you have to be able to do all the integrals. In the end, I have 64 pi divided by 3. Okay? So for divergence theorem, our requirement is, yeah?
So this one, since there are numbers, you can still change that one?
Yeah, you can change whatever order you want, as long as these are all numbers. Right? And that's essentially what I did here. So I just did the integral with respect to these 3 variables separately, and then I multiply them together. Okay? Questions? So divergence theorem comparing to Stokes theorem is much easier to implicate, especially if you go from this direction. You use triple integral to evaluate surface integral. The surface integral in some cases are pretty hard to evaluate. And then divergence theorem is going to be pretty easy to implement here. One small remark I want to make. If the divergence of a vector field is equal to, on a constantly remind you of the different notations, is equal to 0. If this is equal to 0, we have a word for those kind of vector field. If the curl is equal to 0, we say it is irrotational and it is therefore conservative. If the divergence is equal to 0, what's the word I assign? Incompressible, right? Incompressible. In a book, it's actually called a source free. Okay? Incompressible is actually much more widely used in literature. Incompressible actually means there's no source, there's no sink. Okay? You cannot generate for this kind of vector field following a particular vector field satisfying this equation. You cannot sink in more fluid if your fluid is flowing with respect to this vector field. So in other words, it is incompressible. Okay? So in this case, all the the triple integral of the divergence is equal to 0 because this guy vanishes identically. Right? Therefore, the surface integral of the vector field along any closed surface is always equal to 0. So this implies the surface integral of the vector field or the flux of the vector field on any closed surface is always equal to 0 if S is closed. Okay, so this is a small remark I want to mention, which you might be able to see this in a lot of chemistry, physics, or even engineering problems. When they talk about a vector field is incompressible or source-free or sink-free, it's actually talking about the flux over any closed surface is always equal to 0. And that is equivalent to saying the divergence theorem. Okay? Now I want to give you one more question, which is slightly more complicated than this one. So I still have a vector field, which is z minus x squared y, x squared y plus x cubed, 2xyz. And the domain is bounded by 0 is less than equal to x, less than equal to 3, 0 is less than equal to y, less than equal to 2, and 0 is less than equal to z, less than equal to y. Okay? So this is the domain, which means I want to compute the surface integral of f dot s, where this s is the boundary of D. Okay, so this is our problem. We we want to compute the surface integral of boundary of D. First of all, if I ask you this domain, which type of domain is this in terms of triple integral? It's a z simple, and in the xy variable is simply a right angle, right? Simply just a right angle. So the only thing you need to worry about is the z variable. However, even this domain seems pretty easy. Graphing it is not quite trivial, right? If you want to try to graph this, to see where the surface is, right? So the surface as the boundary of this domain is going to be a collection of planes, right? It's going to be a collection of planes. Remember, these guys are all planes, and these are also bounded on the xy plane. So you're getting a whole bunch of planes as the boundary of this region, which means if you want to proceed to take the surface integral as it is, you need to divide it into each one of the plane with the corresponding normal, and then you need to sum them together, which is not easy, right? But now we have to call up our best friend now, which is the triple integral. So I want to do a triple integral of the divergence of the function dv. And I know this domain is simply a z simple region, right? So I wanted to do an integral from 0 to 3, 0 to 2, which means z equals inside 0 to y, and the divergence of this function. This is your f, this is your g, and this is your h. One thing I want to mention, if you go to our final and you go to any midterm, or any of your future career, if you see your function to be polynomials, no matter how complicated it is, there's no problem, you can solve everything. Are you with me? If every function is a polynomial, there's nothing you need to worry about. Okay? You can take derivative, you can take integration, everything will just follow naturally. There's a fixed rule to take integral and derivatives of polynomials. You can always find everything. You don't have to worry about anything. So something will happen, radical functions will create a problem. If you have complicated exponential functions, that will create some problem. Trigonometric functions might create some problem. Rational function, in a lot of cases, will create a problem if you have denominator. But polynomials, you don't have to worry about anything. So once you see a problem have polynomials, the computation might be complicated. You might need to do some messy computation. But overall, there's no